Section. In this section, we observe that deep learning is increasingly favoring larger model architectures, as seen with models like GPT-4, DALL-E 3, and LLaMA3. These larger models can fit vast datasets perfectly, often memorizing the data with almost no loss. However, the Empirical Risk Minimization framework does not prioritize among the many solutions that can fit the data. Thus, the practical solution we find depends on both the learning framework and the biases of the optimization algorithm we choose. For example, stochastic gradient descent plays a crucial role in guiding towards models that generalize well. While much research has focused on optimizing algorithms for we note that exploring alternative learning frameworks has not received as much attention. These alternatives might be more suitable for specific scenarios, especially when we need to optimize for factors beyond average performance, such as uncertainty, fairness, or robustness. Given the many well-generalizing solutions available in modern machine learning, we question why we would limit ourselves to those derived from In this paper, we introduce a new learning framework called feasible learning, FL. We frame learning as a feasibility problem, aiming to find a predictor that meets a specific loss constraint for all training samples. Unlike which focuses on average performance, Florida requires a minimum performance level for each data point. Specifically, Florida sets up an optimization problem with a constant objective function while imposing a constraint on the loss for each training sample, where the maximum allowed loss is a non-negative value. The key features of Florida include: 1. It is sample-centric, ensuring satisfactory performance across all training samples, unlike which may overlook individual sample performance. 2. Florida does not favor any specific feasible models. It accepts any solution that meets the minimum performance threshold for each data point. 3. Florida encourages functional regularization of the loss function, helping to prevent overfitting. We illustrate FL's behavior through a polynomial regression task, showing that both and Florida can find good solutions, but Florida can yield different predictors. The existence of non-interpolating solutions is a characteristic of FL, but finding them depends on the optimization algorithm we choose. We utilize a primal-dual optimization approach to solve Florida problems, which involves a weighted version of where the weight for each sample corresponds to a Lagrange multiplier that adjusts based on the difficulty of fitting that sample. This approach is beneficial because it allows us to use established techniques for training deep neural networks, scales well to high-dimensional problems, and does not inherently favor interpolating solutions. A challenge we face with Florida is determining an appropriate constraint level. If set too strict, the problem may have no solutions. If too loose, it may not ensure good performance. To tackle this, we introduce slack variables to make the problem feasible, which we call resilient feasible learning, RFL. Our primal-dual method for RFL offers better convergence guarantees than for Florida. To deepen our understanding of feasible learning, we address several questions. 1. Can we learn using Florida? Yes. Deep networks trained with Florida achieve similar average performance to on both training and test sets, with comparable training costs and hyperparameter robustness. 2. How does RFL help? In cases where Florida struggles with infeasibility, RFL improves performance. 3. How do Florida solutions compare to We find that Florida results in a more concentrated loss distribution, leading to fewer instances of excessively high losses. Our main contributions include proposing feasible learning as a constraint satisfaction problem, introducing resilient feasible learning to address feasibility issues, and providing algorithms for solving both Florida and RFL problems that are efficient like gradient descent on We also conduct empirical explorations of Florida and RFL, supporting our findings. In summary, we present Florida, offer a practical algorithm for it, and provide evidence that Florida is a strong alternative to the traditional framework. However, we do not claim that Florida outperforms or other learning methods. Balancing competing objectives in multi-objective problems depends on specific applications and requirements. Future research should explore which statistical goals Florida is best suited for, while we focus on empirical exploration and property investigation of Florida. Section Summary. In this section, we introduce feasible learning, FL, a novel framework that formulates learning as a constraint satisfaction problem, requiring a minimum performance level for each training sample rather than optimizing for average performance as in empirical risk minimization, ERM. We also present resilient feasible learning, RFL, which addresses potential infeasibility in Florida, and demonstrate through empirical exploration that Florida and RFL can achieve comparable performance to ERM while offering distinct advantages in handling individual sample losses. Section: Feasible Learning. In this section, we address the task of learning a predictor that maps input data to output labels using a set of parameters on a labeled dataset. We evaluate the prediction quality using a loss function that measures the difference between the true labels and the predicted values. For simplicity, we denote the loss for each data point and its vectorized form. The feasible learning, FL, approach focuses on solving a feasibility problem, where we aim to meet a loss constraint for each training sample while keeping the objective constant. A model is considered acceptable if it maintains a loss below a certain threshold for all training points. By using squared error as our loss function, we can limit the maximum error for each sample, while using cross-entropy helps ensure the model assigns a reasonable probability to the correct label. When our model can perfectly fit the training data, setting the threshold to 0 leads to solutions that achieve zero loss on all samples. However, if we allow a positive threshold, we can find additional solutions that meet the constraints without necessarily fitting the data perfectly. In cases where the model cannot interpolate the data, we may face challenges in selecting the right threshold, as too tight a value can make the problem infeasible, while too loose a value may not ensure good performance. We also explore how Florida does not inherently prefer solutions that fit the data perfectly, introducing a form of functional regularization. This means we do not push the loss below a certain threshold, which differs from traditional regularization methods. When we solve Florida problems, we encounter non-convex optimization challenges, as the loss function may not be convex in the parameters. We utilize Lagrangian duality to tackle this, defining a min-max game where we optimize both the model parameters and the Lagrange multipliers associated with the constraints. Our algorithm alternates between updating the model parameters and the multipliers, dynamically adjusting the importance of each data point based on their loss. We note that the optimization process does not aim to reduce the loss below the specified threshold. Once a constraint is met, the corresponding multiplier is reduced, which prevents further loss minimization for that sample. However, we must be cautious of overshooting into the feasible region, which can be managed by using proportional integral, pi, controllers for updating the multipliers. In cases where the problem is infeasible, the multipliers for unsatisfiable constraints may increase indefinitely, leading to instability. However, our method for solving these problems avoids this issue. We find that the cost of our approach is efficient, as the direction for updating the model parameters can be computed without storing individual gradients. This makes our method comparable in efficiency to standard gradient descent techniques. Finally, we highlight that while more advanced optimization techniques exist, we prefer alternating updates for better convergence without added computational cost. Our approach is well suited for mini-batch processing, allowing us to efficiently sample data, update multipliers, and perform stochastic gradient steps for the model. Section Summary. In this section, we explore the feasible learning (FL) paradigm, which focuses on learning a predictor by solving a feasibility problem with a constant objective while enforcing loss constraints on training samples. We discuss the optimization dynamics involved, including the use of Lagrangian duality and the role of Lagrange multipliers in dynamically re-weighting data points based on their loss, ultimately highlighting the trade-offs in selecting constraint levels and the efficiency of our proposed methods for solving Florida problems. Section: Resilient Feasible Learning. In this section, we address the potential issues with feasible learning, FL, by introducing resilient feasible learning, RFL. We do this by relaxing constraints using slack variables, which we denote as U. When we have a positive alpha, we can formulate a constrained optimization problem. RFL is robust against problems that may be incorrectly specified. If the original Florida problem is feasible, the RFL problem will be the same, as the optimal slack variables will be 0. Importantly, RFL ensures that a feasible solution exists, even if the original Florida problem does not. We prefer RFL in practice because it simplifies the challenge of setting epsilon. Here, a positive slack variable indicates a relaxed constraint, while a 0 slack means the constraint remains unchanged. The cost of relaxing these constraints is based on the norm of the slack variables, and we focus on the L2 norm for its algorithmic benefits. While we could set epsilon to 0 to find the tightest loss requirements, keeping epsilon positive allows for regularization, similar to Florida. This helps prevent the model from excessively minimizing losses per sample, even if some data points violate constraints. For instance, epsilon might require nearly correct predictions, while the slack variables allow for some misclassifications. Although the parameter alpha does not alter the optimal solution, it influences the algorithm's dynamics. We present a formulation with an arbitrary alpha to provide flexibility in tuning these dynamics, which we explore in our results. To solve RFL problems, we use the Lagrangian approach, similar to Florida. We transform the Lagrangian problem to eliminate slack variables. The strong duality condition holds for every theta, allowing us to solve the Lagrangian problem through a quadratically regularized version of the Florida Lagrangian. This formulation is beneficial because it guarantees convergence for non-convex, strongly concave min-max problems. The strong convexity of the function leads to a linear convergence rate. The updates we perform are similar to those in primal-dual Florida, with the primal update direction remaining consistent. The dual update includes a weight decay that prevents multipliers for unsatisfiable constraints from growing indefinitely. We analytically solve the inner maximization problem, leading us to a result that allows us to approach the problem as either a non-convex, strongly concave min-max problem or a non-convex ERM-style minimization problem. We prefer the primal-dual approach due to its advantageous optimization dynamics. In our experiments, we evaluate the feasible learning framework, showing that both Florida and RFL provide a strong alternative to the commonly used ERM framework. We demonstrate that models trained with Florida can learn effectively and highlight the advantages of RFL over Florida, analyzing their loss distribution profiles. We train RESNET18 models for CIFAR10 classification and UTK face age regression, fine-tune an 8 billion parameter LLAMA 3.1 model on a clean dataset, and train a multi-layer perceptron for 2 moons classification. Each task's training set size corresponds to the number of constraints, and we interpret the constraint level epsilon in terms of loss. For classification, we bound the cross-entropy loss, ensuring a lower bound on the predicted probability for the true class. For regression, we bound the squared error, which measures the difference in years between predicted and true ages. We normalize ages to have 0 mean and unit variance. In direct preference optimization, DPO, the loss constraint is expressed in terms of the difference in rewards for preferred and dispreferred completions. We train models using various methods, including ERM, clamped and squared ERM, Florida, and RFL. We report metrics averaged over 5 seeds, using PyTorch and the Cooper library for constrained optimization, with experiments conducted on NVIDIA L40S GPUs. Section Summary. In this section, we introduce Resilient Feasible Learning, RFL, which enhances the robustness of feasible learning, FL, by incorporating slack variables to address potential misspecifications, ensuring a feasible solution even when the original problem is infeasible. We demonstrate the advantages of RFL over Florida through empirical evaluations across various tasks, highlighting its effectiveness in managing constraints and improving model performance. Section: Can we learn with feasible learning? In this section, we evaluate models trained with feasible learning, FL, using the main success measure of empirical risk minimization, ERM, which is average performance. We recognize that Florida addresses a different problem, but we still want to see if it can perform well in standard learning tasks. Our results for a CIFAR 10 classification task show that both Florida and Robust Florida, RFL, can learn classifiers effectively, with only a slight drop in average performance compared to ERM on both training and test sets. We also note that Florida and RFL might have benefits in terms of tail behavior and robustness, making them appealing for specific applications. We find that Florida and RFL achieve performance similar to ERM within the same training budget of 200 epochs. However, we must be cautious with the dual step size. If it is too small, convergence slows down, and if too large, performance suffers. Despite introducing a new hyperparameter with the dual step size, we observe that Florida and RFL are quite robust to the choice of both primal and dual step sizes, maintaining good performance across various scales. Next, we conduct an ablation study on RFL's alpha for the UTK face age regression task. We set epsilon to 0, which is unattainable due to duplicate samples with different labels, to highlight the advantages of resilience in meeting constraints. We find that FL's constraints are too strict, leading to poor performance compared to ERM. In contrast, RFL can relax these constraints and achieve comparable performance, even outperforming ERM in average training and testing errors. Although RFL allows for larger maximum errors than Florida, it still achieves smaller maximum standard errors, indicating FL's limitations. We also see that RFL is not very sensitive to the choice of alpha, but selecting an appropriate alpha may require extensive tuning. When comparing Florida solutions to ERM, we analyze the loss distribution. We find that for small losses, ERM has a higher proportion of low-loss samples, while for larger losses, Florida performs better, indicating more consistent performance, especially in challenging cases. Florida also shows lower average losses for high-loss samples, making it valuable in scenarios where consistent performance is crucial. We also explore the informativity of multipliers, which can indicate the difficulty of meeting constraints. In a 2 moons classification task, we see that samples near the decision boundary have larger multiplier values, suggesting they play a significant role in shaping the classifier. Conversely, easy-to-classify points have near-zero multipliers. We observe similar patterns in the UTK face age classification, where some samples can have small losses but large multipliers, indicating they were challenging to fit. This suggests that we can identify outliers or difficult samples that may not be apparent from the final loss alone. Additionally, we notice that many samples have 0 multipliers towards the end of training, especially with RFL using small alpha values, implying that the updates rely on a small subset of the data. This insight could help improve computational efficiency by pruning easier samples from the dataset.